Before we wrap this up, we have one more MST algorithm to do, and that's Kruskal's algorithm. Okay, so recall earlier I said Prim's algorithm works on nodes, and Kruskal's algorithm essentially works on edges. Okay, so let's take a look at the example we ran before. So I'll just copy this example down just as it was. A, B, C, D, E, F. And we have no edges here, 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 and here, and here. So that's 3, 4, 5, 3, 4, 5, 1, 3, 2, 3, 3. And notice the following. You can think of a spanning tree as a connected graph that has exactly v minus 1 edges. Okay, so note. A spanning tree always satisfies the following. So it's always connected. Right, that's critical, right? It has to contain every single node and allow a path from every node to every other node. And 2, the size of the edge set is equal to the size of the vertex set minus 1. Okay, so recall what our MST was in this graph. Well, it was, or one of our MSTs anyway, looked like this. Contained that one. Not that one. Let's see if I can pull this off. Yes, it's pretty close. Yeah, I believe that was our MST. Whoops, no, I like it red. So this was our MST. What am I missing? Yeah, this is an MST. I don't know if this is the exact MST we had before, but this is an MST. And so this MST, if you count up the edges, we've got 1, 2, 3, 4, 5 edges and 6 nodes. And it turns out one of the ways of characterizing a tree is as a graph that satisfies this, that is acyclic. Okay, and so we actually need the last connection here that says, or the last property here that says it's acyclic. Okay. So what Kruskal's algorithm does is it says let's exploit this characterization of a spanning tree in a way that selects small, low weight edges. So what Kruskal says is let's start with nothing. Let's start with an empty graph, and then let's add edges one by one in increasing order of their weight, right? So we'll start by adding small edges, and then we'll kind of grow to adding larger and larger edges as time goes on. And let's just make sure that we maintain these properties. So we'll add exactly v minus 1 edges. We'll make sure that we keep that eventually we make the graph connected, and we'll make sure that at every step we don't create a cycle. That's Kruskal's algorithm. So here let's run through an example of Kruskal's algorithm. It's quite simple to see how this works. There are some implementation details, by the way. I'm not going to go through, but you can read about them. You can read about them in the book if you're interested. So what does Kruskal's algorithm do? Well, first it writes down the edges in order of their weight. So here's the list of all edges. Okay, so we start with DE, has a weight of 1. CE and AD have weights of 2 and 3. CE and AD have weights of 2 and 3. So that's CE and AD. The other edges that have weights of 3 are BC and CF. 3 and 3, BC, CF, and then EF. 3. And then we have some 4, so AE, BE. 4, BE, 4, and then AB is 5. So what Kruskal does is it walks down this list, adds edges one at a time to the graph. Right? Starts with an empty graph with only nodes and no edges, and it adds edges to the graph one at a time in order of their weights, and just guarantees that every time it adds an edge, it doesn't create a cycle. Okay, so the implementation issue that we need to worry about, which I'll leave for you to study on your own, is to make sure that we don't create a cycle, right? But as long as, as we work through a simple example on our own, we should be able to see when cycles are being created. Okay, so the first edge we add is this one, right? We'll always add the lowest weight, right? So there we add that edge. And then we look at CE and we say, does CE create a cycle? If it does not, and here it can't because there's only two edges in the graph. If it does not, then we'll add it. So CE gets added, okay? And now we look at AD and we ask, does AD create a cycle? And AD does not, so we add it. So we've added so far these three edges. So now notice we can only add 5 edges, right? Because the ultimate spanning tree only has 5 edges because there's 6 nodes. So now there's only 2 more edges to add. So now let's look at BC and ask, does BC create a cycle? And the answer is it does not. So let's add BC. So now we've added BC. Now we look at CF and we say, does CF create a cycle? And it does not, so we add it. And there's our spanning tree, right? So now we've added all the nodes, and we're done, right? We've just created a spanning tree, and so notice that it's possible that we could have done this in a different order that did create a cycle, right? We could have looked at EF earlier. If we had looked at EF earlier, then we could have run into this potential of creating a cycle here. In which case, we would have just skipped any edge that would have created a cycle. And so this is Kruskal's algorithm, right? It's really quite simple to think through, and the proof of its correctness can be obtained through an inductive argument, kind of similar to what we did with Prim's algorithm as well. And so for Kruskal's algorithm, I'm not going to go through the formal correctness argument. I'm also not going to go through the formal complexity argument. But I wanted to make sure that you had seen Kruskal's algorithm at some point, just so that you have this kind of in your arsenal as well going forward. And then part of what you're going to do on your homework is you're going to compare Prim's algorithm and Kruskal's algorithm on different types of graphs. So I'll pose for you a notion of graph density, kind of how many edges a graph has, and I'll tell you about the different complexity classes of Prim's algorithm and Kruskal's algorithm, and I'll let you explore how to use the algorithms to kind of optimally solve the MST problem on various kinds of graphs.